Hi guys, welcome back to the channel. Today we'll be continuing our discussion about threads. In the last video we talked about mutex and saw how a mutex unlock and lock around the critical section of the code prevents simultaneous access to the shared variables by multiple threads. In this video we'll talk about condition variables, why they are needed and what problem do they solve. We'll also talk about notion of signal and wait in context of conditional variables. So let's get started on this one. Before we dive into what condition variables are, we need to understand why were they needed. To understand that, let's discuss a producer consumer scenario. On the left is the producer code and this is the consumer code. Producer, by doing an increment on the shared integer variable avail, depicts that the unit has been produced, whereas on the other hand, consumer, by doing a decrement on this shared integer variables, depict that the produced unit has been consumed. And since this integer variable is shared amongst both the producer and the consumer thread, there has to be a pthread mutex lock and unlock in both producer and the consumer around the critical section of the code where we access the shared variable. Let's look at the producer code. Producer takes a mutex lock, increments the integer variable to depict that a unit has been produced, and does a pthread mutex unlock. Once the mutex has been unlocked, consumer can have a chance to run. It has an infinite for loop inside which it does a mutex lock in preparation of checking the shared variable. Avail greater than 0 is the test condition for this loop. If there are available units, then all the units would be consumed until there are no more units, at which point the control will break off from this while loop and do a pthread mutex unlock. The producer can then acquire the lock and produce a unit which consumer would consume in the next context switch. The problem with such kind of methodology is that consumer spins inside this infinite for loop checking for the produced unit. To understand the point that I'm trying to make, let's see a scenario where avail is 0 and producer has not produced any unit yet. Consumer starts running, goes into this infinite loop, does a pthread mutex lock. Once the pthread mutex lock has been executed, producer cannot run. It would simply block on this mutex lock call. Let's come back to the consumer where it checks for the shared variable avail to be greater than 0, which it is not as per our current scenario. It moves out of the while loop, does a pthread mutex unlock, and loops again as per the loop condition. It would again do a pthread mutex lock, check for the avail integer variable, do a pthread mutex unlock, and keep spinning in this for loop. Yes, I agree there could be scenario where a context switch happens maybe here or just before consumer has locked the mutex and producer produces a unit and then consumer would consume the unit. But still there can be scenarios where avail is just equal to 0 and consumer keeps spinning in this for loop again and again checking for this available produced unit. To remedy such kind of situation, condition variables come in handy. With condition variables, we have a notion of signal once the unit has been produced. Once the unit is produced, the consumer is signaled and then it can consume the unit instead of doing a infinite spin checking the available integer variable again and again. This saves lot of CPU cycles which are unnecessarily wasted while looping inside this for loop and checking for the available unit. To prevent the CPU from unnecessarily spinning inside this for loop and checking for the available integer variable to be greater than 0, we can have a conditional wait where we pass the condition variable and the mutex. I'll explain in the next slide why we need the mutex here. As soon as I do a condition wait call, condition variable has not been signaled, this call will block. Now the consumer will be blocked on this condition wait call, and as soon as producer produces a unit, it will issue a signal call on this condition variable. As soon as signal is executed, conditional wait will unblock and proceed ahead consuming the available produced units. We can allocate a condition variable statically, similar to how we were doing mutex allocation. This initializer is available in pthread.h itself. This is the pthread condition signal call where we pass the condition variable, and this is the pthread condition wait call where we pass the condition variable and the mutex as well. It is important to note that mutex is needed in wait call whereas it is not needed in the signal call. Let's look at this example again to understand why do we need mutex in the wait call. Let's look at the flow of this program from consumer's perspective. Consumer would kick in, take the mutex lock and reach this condition wait call. Condition wait call does three things atomically. It unlocks the mutex first, checks for the condition variable in the next step. If the condition variable has been signaled, it relocks the mutex and proceed accessing the shared variables because there is some work to do as a signal call was executed. Otherwise, if it has not been signaled, then it goes back to sleep and stays in the blocking state until condition variable has been signaled. Unlocking the mutex is important because before issuing a condition wait, we have already locked the mutex. Only once the mutex has been unlocked inside the condition wait call can the producer kick in, take the mutex and produce a available unit. If the mutex is not unlocked, producer can never take the lock and produce a unit. So unlocking the mutex is an important step that happens inside the condition wait call atomically. It then checks for the condition variable, and if it has not been signaled, it sleeps and blocks until the condition variable is signaled. Otherwise, if the signal has already happened, it would relock the mutex and consume all the produced unit, and before leaving the critical section it would unlock the mutex so that the producer can again take the mutex and produce some available units. It is also important to note that this signal could have happened after the mutex unlock as well. If we do a signal after the mutex unlock, then the mutex locking that happens within the condition wait would happen immediately. However, if the signal has been done before the mutex unlock, then the mutex lock inside the condition variable would again block. The producer would first unlock the mutex, and then the relocking inside the condition wait would pass, and then we can proceed ahead and consume all the available units. With pthread condition signal, we are guaranteed that only one of the waiting thread would be awakened. However, with pthread condition broadcast call, all the threads are awakened. To understand this better, let's take an example where there are three threads and all of them have invoked condition wait. If a producer thread does a condition signal, then any one of this T1, T2, T3 threads would be awakened. It will consume all the available units, and all the other threads will continue waiting on the condition variable, maybe for the next signal. However, if the producer does a broadcast, then all of these threads would be awakened, but one of them would be scheduled to run first. It would consume all the available units and then go back to sleep. If T2 and T3 are also designed to do the same task, then they are also going to be awakened, but they will see that the avail has already been consumed by T1 and there would be no work left for T2 and T3, so they'll not do anything. Condition signal can be more efficient as compared to condition broadcast if all the threads are designed to do the same work, because in broadcast all the threads wake one by one, but one of the threads would have already done the work and there would be nothing left for the other threads to do. Condition signal and condition wait return 0 on success and a positive error number in case of error scenario, just like all other pthread calls that we have discussed until now. Let's now look at an example program. We are going to implement the program first without the wait and signal call, and we'll see that the consumer is unnecessarily spinning inside the for loop, checking for the reduced unit again and again. And in the second variation, we are going to add the condition wait and condition signal calls, and we'll be able to see consumer in this scenario will not spin again and again and would simply block on the condition wait call. Inside the consumer, I am looping infinitely and consuming all the units once I see avail is greater than 0 inside the while loop. There is a mutex unlock before leaving the critical section. Consumer would increment the shared variable to depict there are produced unit. The increment would lie inside the mutex unlock and mutex unlock call to prevent simultaneous access to the shared variable. We are now going to launch both the producer and the consumer thread from the main. We'll also join both of the threads before the main program exits. I have added print statements to better understand the program. We can see the consumer is producing the unit and the consumer is consuming them. But once all the units have been produced, we'll be able to see consumer still trying to loop inside the loop and checking whether there is something to consume. I'll remove this sleep so that you can see infinite loop in action. Uh, the consumer is looping inside infinitely, checking the available integer again and again. We are now going to add a condition signal and a condition wait. Let's define a static condition variable using the condition initializer available inside pthread.h. We'll add a condition signal just after the unit has been produced to let the consumer know that there is some work to be done. Inside the consumer, we are going to add a condition wait and pass the condition variable as the first argument and mutex as the second argument. State of the shared variable should never be assumed after the condition wait has unblocked. That is why we are going to add condition wait inside a while loop, where we check for the state that we want the shared variable to be in. Let's run the program now and see how the consumer behaves. We can see producer is producing the unit and consumer is consuming them one by one. Once the producer has finished producing 10 units, we can see that the consumer has blocked. It is not checking for the available unit again and again as we saw in the previous scenario, where there were a lot of prints on the console where consumer was looping infinitely. In the next video, we can take a look at few basic thread programs like printing odd and even numbers using a multi-threaded program and using thread pool to solve some task by allocating a task to each thread.